We have previously analysed simple problems, such as a square potential barrier, and we have been able to write down quite complete results for reflected waves, transmitted waves, and the associated waves or exponential decays inside barriers. In principle, we can extend these simple methods to structures with multiple layers. In practice, we need better mathematical techniques to keep track of the various coefficients that come up in such structures. Fortunately, there's a very straightforward way of doing that. The method we will introduce here uses what is called the transfer matrix. Essentially, we're able to use the matrix notation and matrix algebra to keep track of all of the various waves and coefficients. This use of matrix techniques also means this approach is particularly simple to implement in computer programs. Almost any computer language or mathematical software can handle this method quickly and efficiently. This method is, incidentally, also widely used in optics for calculating the behavior of waves in multiple layer structures. Optical coatings used to make mirrors and beam splitters and filters and anti-reflection coatings are often based on multiple layers of transparent dielectrics. This same approach can also be used to analyze simple optical waveguide structures. Here, we will introduce it for the quantum mechanical case. We could handle the optical case simply by using the different boundary conditions we would get from Maxwell's equations.
We presume that the potential then is a series of steps. This could be an actual step-like potential, such as the following. Or we could be approximating some continuously varying potential, such as this smooth line here, and we're approximating it by a series of steps that correspond to roughly the position of where the line crosses the center of these steps, something like that. We therefore reduce the problem that we're trying to solve to that of waves within a set of simple constant potentials, and inside those constant potentials the waves are either sinusoidal or exponential, together with appropriate boundary conditions as we go from one layer here to another. And we know how to solve any one of these little problems here, and we would be able to link the solutions in the adjacent layers. So we could be looking at a structure that we use a nomenclature like this to describe. We could number all the different layers in the structure, and I've chosen to number them starting by labeling this layer as layer 1. This layer we take for our modeling purposes to be infinitely thick over towards the left, and this layer we take to be infinitely thick over towards the right. So I've labeled this one layer 1. There are n layers in the actual structure, and I've called this layer n plus 2. I've also labeled the interfaces. This is interface 1 all the way up to interface n plus 1 for our n layers here. There are other numbering schemes you could use. One might want to start this with layer 0, for example, but this scheme here will work, and I will use this consistently throughout the algebra, and you might find therefore that this is a good one to use if you choose to implement this scheme yourself. Then you'll be able to relate it to the algebra that I will present to you. So we're going to consider an electron wave incident on a structure like this from one side, the left here, with a particular energy E. So here's our instant wave, we imagine. There will be reflected waves, and there will be transmitted waves. For each layer in the structure, what we can do is derive a matrix that relates the forward and backward amplitudes. For example, here, just to the right of a given interface, just to the right of some interface here, and to the interfaces just on the other side of the next layer. So we could be relating the amplitudes here to the amplitudes just here, for example. So amplitudes AM and BM will be the forward and backward amplitudes in layer M, and amplitudes AM plus 1 and BM plus 1 will be the forward and backward amplitudes in layer m+1. In each case, we'll choose to define those to be just to the right of the interface with this index. And what's going to happen is that by multiplying those matrices together for all the layers, we're going to construct a single transfer matrix for the whole structure. And that will enable us to analyze the entire multi-layer structure. So we're going to use matrix algebra here to help us handle this more complicated problem. So in this formalism, each layer will have a potential energy, Vm. So here are my various potentials here. In this case, we will probably choose V1 and Vn+2 to be the same. And a thickness, dm. So the thickness of layer 2 is d2, the thickness of layer 3 is d3, and so on. As I said, layer 1 is supposed to be infinitely thick in this direction, and layer n+2 infinitely thick in that direction. And then also each layer may possibly have a mass or effective mass that could be different for each layer. So we can give those labels and numbers associated with them as well. For interfaces 2 and higher, the position of the mth interface relative to the position of interface 1 would just be as follows. For the position of this interface 2, well, it would just be a distance d2 from interface 1. Interface 3 would just be a distance d2 plus d3, and so on. So formally writing that out as a summation, in the notation I'm using here, the position of the mth interface would be the sum from q equals 2 to m of these distances dq. That's very straightforward, but algebraically it's useful to have an explicit expression for that. Now, in any given layer, if the particle energy E is greater than the potential energy in that layer, we know that we will have, in general, both a forward propagating wave in this kind of form and a backward propagating wave in this kind of form. And in this algebra here, for each different layer, I'm going to refer the distance relative to the position of the interface to the preceding layer. It's up to me how I choose to define this. It makes no difference to the end of the problem, but it does change the algebra, and I'm going to make this as my algebraic choice. And of course, A and B are complex numbers for the forward and backward wave amplitudes. In this case, Km, the wave vector, will just be the square root of 2mfm, the mass in this layer, divided by h bar squared, times E minus Vm. So this will be a real number. It will be the square root of this. We could choose to take the positive square root, which is what we will do here. And this will work when E is greater than Vm, because this will be a propagating wave. And as I said, mfm is the mass of the particle in that layer. If the particle energy is E less than Vm, we know we will have, in general, both a forward decaying wave, so that's a wave doing this kind of thing, and a backward decaying wave, which is a wave doing this kind of thing, or technically it's growing in the forward direction mathematically. And again, A and B are complex numbers for these forward and backward wave amplitudes. I use wave loosely here. These are not technically propagating waves in this case. And in this case, we could define a kappa, again, as the positive square root now of Vm minus E, in contrast to the E minus Vm that we had for K. And again, mfm is the mass of the particle in that layer. Now, this is a perfectly good way to do the algebra, but it turns out to be simpler if we do something slightly different. For the case of E less than V0, so that's where we don't have propagating waves, we could still mathematically use this same formula. So we could talk about a k value that was still the square root of E minus V. Now, this would give us an imaginary Km. But it turns out that algebraically that works just fine. As long as we choose a positive square root all the time, either a real answer or an imaginary one, in both cases, we can work with only this expression. For example, a forward propagating wave can then be written in the form e to the I km z minus zm minus 1. For both cases, both the real propagating waves and the growing or decaying exponentials. So, no matter whether e is less than v0 or e is greater than v0, and similarly for the backward propagating wave, we can use this one formula. If k is an imaginary number, then this, of course, turns into just a negative real argument in the exponential. Now, in any layer, we have a wave that we can write, therefore, as some forward amplitude, e to the I km z minus zm minus 1, plus bm e to the minus I km z minus zm minus 1. And as I say, here k can be either a real or an imaginary number. This will work perfectly well algebraically. And as I said, we're going to choose to define k in this way. And this use only of k and not k and kappa greatly simplifies the algebra for this method. It doesn't matter if we do this, we can still solve the problem without doing this, but this simplifies things. Okay, so let's look at the boundary conditions that we're going to work with here. And specifically, we're going to look at the boundary conditions in going from just inside one layer to the right of the boundary, so that would be here, to just inside the adjacent layer to the left of the boundary. So the boundary conditions will be relating the AL and BL to the AM plus 1 and the BM plus 1. So these AL and BL are the amplitudes just inside layer M, just to the left of this interface. And similarly, these are the amplitudes just inside layer M plus 1, just to the right of that interface M plus 1. For a reason that will become apparent later, we will end up working in this problem from right to left. That might seem counterintuitive, but algebraically that will turn out to be more convenient for us. So, using the notation in this figure here, for the continuity of the wave function at this interface, well, the wave function must be continuous, so whatever is the sum of the forward and backward amplitudes just to the left here must be the same as the sum of the forward and backward amplitudes just to the right here. The sum of the forward and backward amplitudes is the total wave at any given point, the amplitude of it. And for the continuity of the derivative of the wave function with respect to z on either side of the boundary, well, because of our form of the wave that we chose to write down, when we take the derivative, we get ika minus b. So that comes from the fact that the b is in front of a backward propagating wave, and so the derivative gives us a minus sign in here. So at the right interface, we have AL minus BL is a quantity delta M times AM plus 1 minus BM plus 1. And that quantity is just Km plus 1 over Km. In other words, when we did this derivative here, we got an IKM times AL minus BL, and we got an IKM plus 1 times AM plus 1 minus BM plus 1. And we can divide out both sides by the Km and write the expression in this form. In a layered semiconductor structure, we might choose a somewhat different condition for the continuity here of the derivative. We might use 1 over the mass times the wave function derivative in each layer for our second boundary condition, in which case we could follow through the algebra here and we would obtain a similar expression, but delta M would now also involve the effective masses in here, the masses in these different layers. But otherwise, we could continue to use this delta M in the subsequent algebra. So if we're using this boundary condition, the expression for delta M is this one. So using these two expressions, we have figured out from the continuity of the wave function, that's this expression, and from the continuity of the derivative of the wave function, that gives us this expression. Then we can simultaneously solve these two equations. For example, adding the two of them will eliminate BL. And that would give us AL was AM plus 1 into 1 plus delta M over 2 plus BM plus 1 into 1 minus delta M over 2. And similarly, if we subtracted this equation from that one, we'd be able to write down an expression here for BL in a similar kind of form. Well, these two equations can be conveniently rewritten in matrix form as follows. We can write that AL and BL as a vector here is equal to a matrix DM times AM plus 1 and BM plus 1 as a vector, where that matrix is in this form. In other words, AL, for example, is this vector here, AM plus 1, BM plus 1, multiplied into this top row here. It's AM plus 1 times this term, plus BM plus 1 times this term, and that's exactly what we have up here. So this is another way of writing these two equations, a rather convenient one. And now we have what we could call a boundary condition matrix. So that matrix allows us to relate these amplitudes to these ones. Similarly, we can look at the propagation that relates AM at this side of the layer to AL at that side of the layer. So AM is just inside this layer at this side of the interface M, and AL is just inside this layer at this side of the interface M plus 1, and similarly for BM and BL. For a minor formal reason, we are going to calculate the matrices for going backwards through the structure. So for the propagation in layer M with thickness dm, we have that the amplitude here of the forward propagating wave will be the amplitude there times e to the minus ikm dm. That's the same thing as saying that the amplitude AL would be am times e to the plus ikm dm, a forward propagating wave from the M part here to the L part there. And similarly for the backward wave. Now, these relations can be written also in a matrix form. It's a somewhat more trivial matrix, but it's still a convenient way to write it. So a matrix here relating the AMs to the ALs and the BMs to the BLs, where this is just simply a diagonal matrix. It's a rather simple matrix, but it's convenient to think of it as a matrix here. So we can construct a full transfer matrix T for the structure that relates the forward and backward amplitudes at the entrance layer, just inside the entrance layer on the left, just to the left of the first interface, to the forward and backward exit amplitudes that are just to the right of the last interface. And that transfer matrix would be some matrix here. And that transfer matrix is simply the product of all of these various boundary condition and propagation matrices all the way through the structure. We'll look at that in more detail. Note incidentally that this transfer matrix is in general going to be different for every energy E for which we want to do the calculation. So when we choose E, that determines what the various K's are in each layer, and that gives us a set of matrices here, or a total transfer matrix, that is specific to the energy E we chose. So this transfer matrix, and indeed each of these other matrices here, does depend upon the value E that we have chosen. So in this transfer matrix here, and in this product, we are moving progressively from right to left. We've got a propagation matrix here that would take us from just inside this layer here to just inside the layer on its left. We've got boundary condition matrices that take us just from the right-hand side of an interface to just the left-hand side of the interface. And what we're doing is we're working backwards through the whole structure. We've got forward and backward amplitudes here that we multiply by the boundary condition matrix to get the forward and backward amplitudes just inside this layer. Then we multiply by the propagation matrix to get the forward and backward amplitudes just to the right of this interface. Then we multiply by a boundary condition matrix to calculate the forward and backward amplitudes just to the left of that interface. and so on, working through the structure. And so we're able to relate with this one matrix the forward and backward amplitudes just to the right here, multiplying by all of these matrices one after the other, or equivalently multiplying by the full transfer matrix to get the forward and backward amplitudes just to the left of the whole structure. So we're starting here with an plus 2 and bn plus 2, and we're calculating a1 and b1. By calculating all of these boundary condition and propagation matrices through the structure, multiplying them up to get t, and multiplying by this vector using the transfer matrix to get this one. Well, having constructed this matrix, we can now think about how to calculate tunneling rates through this structure. So we choose an energy E in some structure, and we now are going to be able to deduce the fraction of instant particles at that energy that are transmitted by this entire barrier structure here. As I said, we're going to presume no wave incident from the right in our problem now, so there is no backward wave amplitude on the right. Hence, for incident forward and backward amplitudes A and B, and the transmitted amplitude F, then the matrix equation gives us the following. Our vector on the right is just a forward wave and no backward wave. We're going to multiply it by this matrix here and calculate, therefore, what were the incident and reflected wave amplitudes at the left-hand side. Well, we can see now quite simply that A is T11 times F and B is T21 times F. Hence, the fraction of particles transmitted by this barrier is, using this formula here, 1 minus mod T21 squared over mod T11 squared. We've just cancelled out dividing the mod A squareds out here, so we're just looking at 1 minus mod B squared over mod A squared, which is this expression here. So if we can calculate the transfer matrix for this entire structure at some energy, we can figure out what the fraction of transmitted particles is. This approach is very well suited for numerical calculations. It's very straightforward to program, and it's a very useful practical technique for investigating one-dimensional potentials and their behavior. We can also calculate the wave functions at any point in the structure here. We can readily calculate the forward and backward amplitudes at the left of each layer. Obviously, we know how to relate the amplitudes just inside the n plus 2 layer to the amplitudes just inside the n plus 1 layer at the left by having a boundary condition, then a propagation matrix. And similarly, we have, in general, for any specific layer in the structure, this formula for working out these amplitudes. And given that we know the forward and backward amplitudes just at the left inside layer M, from this expression here, then the wave function at some point z in that layer is the sum of the forward and backward amplitudes, calculating using this kind of expression here. This is our forward propagating wave, this is our backward propagating wave. We can calculate the total wave at any point inside that entire structure at this energy E for which we're doing the calculation. Note that we could also calculate these forward and backward amplitudes as intermediate results if we just progressively evaluate the forward and backward amplitudes for each successive layer, as in this kind of progressive movement through the layer. We could write down these amplitudes each time we do one of these calculations, for example, if we wanted to. Rather than evaluating the full transfer matrix at once, we could just progressively go through the layer, writing down all the wave amplitudes at each layer and then moving to the next layer and so on. And by choosing no inward wave on the right, we can still calculate the transmission probability in this approach from the same expression here. So let's look at an example of a calculation done using this kind of method. So we're going to look at a double barrier structure So there are two barriers here. This one we could solve directly algebraically, but it's getting a bit complicated to do that. So we've got a double barrier structure here. That's our potential energy. And what we're going to do is we're going to plot as a function of the incident energy of the electron, we're going to plot the transmission through the structure. And here's actually the result of that calculation. We see actually two resonances here, and the transmission hits unity on both of these resonances. So as I said, this structure shows a resonance in the tunneling probability, or equivalently the transmission, where the incident energy coincides with the energy of a resonance in this structure. And that resonance corresponds essentially to fitting in integer numbers of half waves inside this structure here. And we also get a resonance up above the top of the structure. It still sees reflection of these barriers here. So this is like a little resonator with mirrors in it. If the barriers were infinitely thick, there would be an eigenstate at approximately the energy where this first resonance occurs. So here's what happens as we keep putting the energy up here. We're seeing the probability density here and the transmission for the corresponding wavelengths. Let's look at that again. So here's the transmission going through the resonance and up to the second resonance here, which actually occurs above the top of the barrier.